or dynamic programming problems where the backtracking is required. One very most popular example of backtracking problem is the tower of an eye problem or puzzle, that we will see how stack is useful in implementing or solving the problem of towers of an eye. Everybody uses the word processor. You perform undo, redo, forward, backward during navigation of pages. All these operations require internally the use of a stack, because how we will how we can undo a operation if it is stored somewhere. Previous operation, undo does the undoing of the previous last operation that you have performed. For example, I have typed the word undo move object. If I press the undo button, first of all it will remove the last typed word object, then it will remove move, then it will remove undo, because we undo performs the operation in the reverse order. So, whereas the ordering we requires in the reverse, then we use the stack. For example, if we want to traverse a single linked list in the reverse order, then also we need to use the stack, because in otherwise the linked list traversal is only possible in the forward direction. If we go on pushing the elements in the stack, then linked list can be traversed in the reverse order. Similarly, in the forward direction, all these operations they require the use of stacks. Next application that we will study, that is the postfix expression evaluation. How what is a postfix expression? Where the operator follows the is used after the operators operands. So, here the plus operator that will operate on the previous two operands, that are 2 and 3. What will be the result? That will be placed here, and this star will operate on the previous two operands, that is 8 and the result of this expression, and this plus will operate on the result of this expression and the 5, then this star will finally operate on. So, this postfix notation does not require any parenthesis, otherwise we need to parenthesize an expression, and if we forget to put some parenthesis, an expression is not fully parenthesized, then it will lead to error. So, in most of the cases we prefer the prefix or postfix notation of expression for to avoid the use of any parenthesis. So, we will see how this expression will be evaluated internally by your computer. For example, first how the program will be written, what will the logic for evaluating this expression. Whenever some operand is encountered, push into the stack. So, 6 is a operand, it will be pushed into the stack, then 5 will be pushed into the stack, 2 will be pushed into the stack, 3 is also operand, it also pushed into the stack. Now, we have encountered plus. Now, this plus is a binary operator, so it will require the popping of 2 operands from the stack. The first thing that will be popped from the stack, that will be 3, then second thing that will be popped from the stack, that will be 2. So, 2 plus 3 is now 5. The whatever is the result, that will be pushed back into the stack. Now, again we will start scanning the expression. The next element in the expression is 8, that will be pushed into the stack. Now, the next character is again operator. Now, it will again require the popping of 2 operands. First operand that will be popped will be 8, and the second operand that will be popped will be 5. This star will be performed, multiplication will be performed on these 2 operand, and result is 40. This will be again pushed back into the stack. Now, again we start scanning the expression, again we encounter a operator, that is plus, that is again a binary operator. So, again 2 pop operations will be done. So, 40 will be popped out and 3 will be popped out, 5 will be popped out, and this plus will operate on 5 plus 40, the result is 45. This 45 will also be pushed back into the stack. And now, again the last element that is left, that is multiplication. This multiplication will again require popping of the 2 operands from the stack. So, first thing that we will pop from the stack, that is 3, then 45. So, result is 47, 48, 48 will be again pushed back into the stack. So, 48 and 6 will be multiplied and the final result is 288. Now, there is nothing in the input expression. So, we have encountered the end of the expression. At the same time, we need to check the status of the stack. If the stack is not empty, this means there is some error in the evaluation, but here the stack is already empty. So, we have completed the evaluation of the expression successfully and the result is 288. So, we can see how stacks are helpful in evaluating a postfix or prefix or infix expression. Another example we will application that we will study, that is the syntax checking, that is in parsing used by the compiler for checking whether a syntax is correct or not. Stack is useful for checking symbol balance. When a closing symbol is found, it must match the most recent opening symbol of the same type. For example, if there is a if then else nested if then else statement, for every else there should be some if, and for every opening parenthesis or block bracket there will be should be some closing bracket. Similarly, in the HTML or XML tags, if we start some tag, there should be some ending tag. So, for in all these situations during parsing, we need to use the stacks, because we need to backtrack to the previous symbol. So, wherever we need any backtracking, the stack is a very the only way out for implementing that operation. Let us see, this is expression, there is a square left parenthesis, then left square brackets, right square bracket, again brace parenthesis, this is a full, this is not balanced, this is balanced. So, to check whether it is a balanced or not, we can use stack. Because simple counting is not enough to check the balance, you can do it with a stack going left from to the right. If we see a left or opening brace, opening bracket, opening parenthesis, simply we push it onto the stack. If we see a right parenthesis, pop the stack and check whether you got the corresponding bracket or corresponding symbol or not. This is a, if after scanning the complete expression stack is empty, this means expression is fully parenthesized, otherwise it is not parenthesized. The condition to check whether the parenthesis or expression is balanced or not, it is syntactically correct or not, that is the checking the status of the stack, it should be empty. So, let us take some example. This is brace A, brace B, closing brace, then C, closing brace. So, what we will do? First we will perform the push operation, again left brace, again push operation, but when we encounter this right brace, we will perform one pop operation, again we encounter this right brace, again we perform the pop operation. Now, stack is empty, this means expression is balanced. In this example, we have two left parentheses, we will perform two push operations, one right parenthesis, the pop operation is only one. So, after scanning, complete scanning of expression, this stack contains a left parenthesis, stack is not empty, this means this is not, there is a syntax error. Similarly, here we have left parenthesis, there is a, we perform the push operation at the right parenthesis, again we perform the pop operation. Now, the stack is empty, again we encounter a right parenthesis, we need to perform the pop operation, but we cannot perform because stack is already empty. So, we get a error condition and this means expression is not balanced. So, stack is a very simple, using very simple algorithms we can check the syntax of any expression or any block which requires some starting and ending tags. With that, one important example of backtracking problem where the stacks are used, that is the towers of Hanoi. This is a tower, there are the discs arranged in this puzzle. There are 3 vertical pegs and several discs that slide on the pegs. The discs are of varying size, initially placed on one peg with the largest disc on the bottom with increasingly smaller ones on the top. The goal is to move all the discs from one peg to another under the following. What are the rules of the game? We can move only one disc at a time. We cannot move a larger disc on the top of the smaller one. So, using these two rules of the game, we need to solve the problem of moving all these disks from this destination peg to this from the source peg to this destination peg through the use of this temporary peg. So, what are the rules of the game? The larger disk cannot come on the top of the smaller disk, and at a time we can move only one disk. So, we can remove only from the one disk that is on the top, that is the smallest disk. So, this disk will go to the destination peg. So, in the first move we have moved this the topmost smaller disk to the destination peg. Now, there are two disks on the source peg and one disk on the destination peg. In the second move, can we move this disk to this peg? No, because rule states that larger disk cannot be placed on the smaller disk. So, what we will do? We will move this disk to the temporary peg that will go to the second peg. Now, each peg is having 3 disks, the source peg is having 1 disk, temporary peg is having the middle disk and the destination peg is having the smallest disk. But we want to move this larger disk on the bottom of the destination peg. So, what is the solution? We will have to move this disk on the temporary peg, only then we can move this disk to the destination peg. So, what we will do in the third move? We will move this disk to the temporary peg. Now, thus destination peg is empty and we can move the largest disk from the source peg to the destination peg. Now, the problem now reduces to the moving of these two pegs to this destination peg through the use of this temporary peg. So, this is a recursive problem. Initially, we will have n is equal to 3, we want to move from source to destination through this temporary peg. At this stage, now the problem is reduced to n is equal to 2 and now the source and destination pegs are changed. Now, the source peg is the temporary peg and destination peg is the same, but the auxiliary peg or temporary peg is the source peg. So, this is a recursive problem and this can be solved with the help of a stack. Now, in the first last move, what we will do, this smaller disk will be moved to this the previous peg and now again each peg is having 3 disks. We can move this disk to the destination peg and lastly we can move this smaller disk on the last peg. So, how many moves are total required? 7 moves. In 7 moves, we have moved the 3 disks from the source peg to the destination peg. This means 3 factorial plus 2 raised to power 3 minus 1. So, solution total number of moves required to solve the towers of Hanoi problem where n with n number of disk, that is 2 raised to power n minus 1. Here the n was 3. So, 2 raised to power 3 is 8, 8 minus 1 is 7. If their disks are 4, we will require 15 moves, 2 raised to power 4 minus 1. So, but this problem can be simply implemented with the help of a recursive program. Hanoi disk minus 1 from top pole to auxiliary to pole. So, this is a simple solution because this function can be written with the help of a recursion and recursion internally involves the use of the stacks. Here each peg is defined as a stack. So, let us summarize before going to the end of the lecture. So, what are the various, what is a stack? Stack is a last in first out data structure. It has got many applications. It involves simple 2 operations, pushing and popping, but before implementing these 2 operations we need to check the status of the stack, because checking of the status of the stack is very important in many applications. One of the important application that we have discussed, that is the syntax checking, parsing, expression evaluation and the backtracking problems like puzzles like towers of the Hanoi. Other important application of the stack that you will study in data structures only, that is the sorting. What is sorting? Arranging the elements in some ascending or descending order. There are many sorting algorithms, but most efficient sorting algorithm, that is a quick sort. Quick sort is a recursive algorithm that also requires the use of the recursion and implicitly the stacks. So, stack is a very important data structure and it is very efficient to implement using the single linked list. I hope you must have understood the various applications of the stack. Thank you very much for the patient hearing.